So a traditional trig function, like the ones that you know, sine, cosine, tangent, are kind of relate to a circular function, right? Because we call, the unit circle, right? So we know that the coordinates of this point are cosine theta, sine theta, okay? When we start talking about hyperbolic functions, instead of being a circular function, it is a hyperbola. So what makes something a hyperbola is it's of the form either x squared minus y squared equals r squared, or it's a subtraction instead of a addition for that, okay? So as you go through this, and what hyperbolas tend to look like is like this is one hyperbola, as is this. Okay, so they're not parabolas. And like parabolas, the side of a parabola continues to curve. There's actually linear asymptotes for a hyperbola that are diagonal, okay? So when we have, so there's like this formal definition of these hyperbolic functions. So if I give you sine h, you would read this as the hyperbolic sine. Or the hyperbolic cosine. Okay? And basically how do you find the sine or the cosine or the tangent hyperbolic, the hyperbolic of any of those of a certain value, you're basically plugging into these exponential functions. Okay, so if I ask you guys, what is the hyperbolic sine of 2? Well, the hyperbolic sine of x is e to the x, so that's going to become e squared minus 1 over e squared, because e to the negative x would be 1 over all over 2. And if I wanted to, I'd probably make this e to the 4th over e squared minus 1 over e squared over 2. And we can kind of turn this into e to the 4th minus 1 on top and 2e squared in the denominator. I think that's a slightly more pleasant way of looking at it. If you wanted to, you could think of this as I'm multiplying the original by e squared over e squared. That's probably an easier way to see it, to get rid of that denominator. And as long as you do it to both the top and the bottom, you're good. Everybody good so far? Okay. What if I asked you to find the hyperbolic cosine of 2? What would that equal? E squared plus 1 over e squared over 2. And then I might multiply that by e squared over e squared. So far, are you guys okay with the idea that we can find that hyperbolic sine or cosine or tangent by just plugging into these kind of formulas for ourselves? Okay? All right. Now, just like other, so circles are x squared plus y squared equals r squared, right? Which in this case would be 1. R squared would be 1 for both of these. And so, like, because x is cosine and y is sine, like, they change sign, basically. Like, here, they change sign, basically. Because here we have this minus sign. So cosine is, that negative relationship between the derivative of cosine and sine isn't there anymore. It basically stems from that. Functions, we have identities, which probably not going to have to use, and we have derivative rules. And so the other thing I'm going to ask you to do is find some derivatives and find some integrals of these hyperbolic functions. But as we go through this, guys, as you'll see, the ones I'm giving you, I'm not giving you like super complex 5 times u sub kind of things, okay? So overall, the derivative of cosine is the hyperbolic sine times u prime. So if I ask you guys what is f prime of x here, just the hyperbolic cosine becomes hyperbolic sine. And then chain rule says I have to multiply by 8. So I'm going to throw that 8 in front from the chain rule. How are we feeling so far? All right, help me with g prime of x. Write down what you think it is. I'll write down what I think it is. You're going to use the derivative rules up here, yeah? And notice that I'm asking you this on a homework assignment, which is in fact open note, yes? So given the derivative rules, I don't think this is a crazy request. How did I do so far? So the derivative of tangent is secant h squared, yeah? Does this feel like a reasonable request, or am I like, you guys are kind of hard to read right this second? Okay. All right, so what about this one? How'd I do? The derivative of natural log is 1 over, right? And then chain rule would give us, and then if I have sine over cosine, that's just tangent. Yes? No? We good? All right. What do you think we would need to do here? Product rule, fit gif. Okay, so that would be hyperbolic sine of x plus x times the derivative of that, which is hyperbolic cosine of x, minus hyperbolic sine of x. So the derivative rules for these are slightly different. It basically, the reason that happens, can we simplify that? Are you guys cool if I call that just x cosine, hyperbolic cosine of x? Okay. Okay. What do you guys think about this one? You want to do u sub? If we need to, yeah, we could say u equals 3x, du equals 3dx. So dx is equal to du over 3, okay? So I got a 1/3 times the integral of secant squared, the hyperbolic secant squared of u du. And then let's see. We could either look and say, oh, the derivative, or the derivative of tangent is secant squared, or the integral of secant squared is tangent. Hyperbolic for both of those. So this just becomes 1/3 times the hyperbolic tangent of u plus c, which is really 1/3 the hyperbolic tangent of 3x plus c. Does this feel reasonable still? Thoughts on this last one? I'll start with you. What do you think we should make u equal to for this last problem?
Root x.
Root x. So du would be 1/2 x to the negative 1/2 dx. Which, if you guys don't mind, I'm going to do a couple of things here. I'm going to multiply both sides by 2 to get rid of that 1/2. And then x to the negative 1/2 is really x square root of x in the denominator. Is this feeling okay? And if that's the case, I now have 2 and du times the hyperbolic cosine of u. What's the integral of the hyperbolic cosine? So now I have 2 hyperbolic sine of square root of x plus c. And I'm done. Are you guys with me that while they come from a complicated place, the derivatives and the integrals and the values of these functions are not super crazy. And you're going to be allowed to use your notes to do these on that one last homework assignment. So if I give you, I don't know, the next 20 minutes to do those bottom 3 questions, would that work?